Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 29, and in this lecture we are going to talk about what is called energy methods to obtain the deformation problem. So, you remember that we have the equations of elasticity, which is a partial differential equation, and we solve it to obtain the deformation of the entire body, right. Then we also derived the equations for beam theory, Euler-Bernoulli beam theory or Timoshenko beam theory, which was an ODE. So, if we can solve the ODE, we can obtain the deflection of the beam. Now, there is another competing method to obtain the deflection, which is the energy methods. You can recall from your first year mechanics course, we could solve the motion of rigid bodies either using Newton's second law or using the minimization of energy, right. And in many cases, when you work using minimization of energy, it gets simpler. Likewise, here also you will see that energy methods is much simpler to deal with for several problems. Okay. So, before we start the energy method, we have to of course get acquainted with some of the concepts required. Okay. So, we will get first familiar with the concepts needed. Okay. So, suppose that we have a arbitrary body and which could be clamped at some point. Okay. And then you may be applying force which could be concentrated load, let us say at point 1 and at point 2. Okay. And suppose I want to measure what is the deflection at another point on the surface of the body or even within the body, if we can measure. Let us say that is the point 3. So, it is going to deflect in some direction, which would be delta. So, what is the relationship between, say for example, delta at 3 and the force at 1? So, what is it that relates the two? Okay. How are they related? Are they linear? Is there some proportionality constant? Okay. To answer that question, let us first have a look at the equations of elasticity. So, we may recall the equation was del sigma x x over del x plus del tau x y over del y plus del tau x z over del z plus the body force is equal to 0. If it is in statics, then you have two more equations, and this has to be supplemented by the boundary condition, right. So, on some part of the boundary you could have sigma times the normal to the boundary, that is equal to the imposed traction, right. So, this is called the traction boundary condition. Whereas, on other part of the boundary, the displacement u itself could be prescribed some u naught. So, that is the displacement boundary condition. For example, if it is clamped at some point, then the displacement of that point is 0. Now, have a look at the nature of this equation. So, we have this equation which is linear in stress. You see sigma, what is the power of sigma in each of the terms? It is 1. So, it is linear in stress components. Correct? But then stress itself is also dependent on strain, and if we confine ourselves to linear stress strain relationship, then stress becomes linear in strain, and finally strain is linear in displacement. Correct? You see last two assumptions, they are assumptions of linear elasticity, that is the domain of our course. So, this holds for linear elasticity. When you do large deformation problem and we talk about non-linear elasticity, then we think of more general stress strain relationship which need not be linear. Likewise, strain and displacement relationship, they are also non-linear, but here both of them are linear. Okay. Similarly, look at the boundary condition, you have sigma times n, and sigma again is linear in strain and strain is linear in displacement. So, everything here, that means equations and boundary conditions are all linear in the unknown displacement. Okay. But then you can recall from first year mathematics, if the equations are linear in the unknown, and suppose that you have a forcing term in the equation, and if you double the force, then the unknown also becomes double. If you triple the force, unknown also becomes triple. That is because the equations are linear, right. So, for example, think of this spring mass problem, mx double dot plus kx is equal to some force f of t. Okay. You see that this equation is linear in the unknown x. So, x suppose is the displacement of the mass, so you have a spring and a mass is attached to one end. So, that is the mass, this is the spring constant k, and this is your x, f is the force applied here. So, because the equation is linear in x, if you double the force, the displacement solution also gets doubled. If you apply f1, you get some solution x1, you apply f2, you get another solution x2, and in the third case, if you apply both f1 and f2 together, then the solution is simply x1 plus x2. So, that means you can also superpose two solutions. So, this tells us if equation is linear in the unknown, then the unknown becomes linear function of force applied. Not only this, superposition also holds. So, superposition also holds. Okay. So, this was with a spring mass system, very simple, but now we are talking about a deformation problem. We have a 3D body which can deform and the equations are partial differential equations, but still it is linear. All this just tells us that the displacement of the body will then also be linear in whatever force you are applying. So, in this case the force that you are applying, what is the external agent applying to the body? That is the body force here, the body force, and through boundary condition we have this traction T naught. These are things which are being applied by the external agent. So, if you double these things, your solution will also get double, and that is all because we have linear equation. Okay. So, coming back to our original problem, what would be the relationship between delta 3, the displacement at point 3 here, and the force that you are applying at point 1 F 1. So, this tells us that delta 3 is simply proportional to F 1. Okay. Now, since it is proportional, there will be a proportionality constant, right. So, we could say that delta 3 is equal to a constant k 3 1 into F 1. So, k 3 1 is the proportionality constant, which is also called influence coefficient. If you change the location of the force 1, so if the point 1 is changed, then k 3 1 will also change. Likewise, the point where you are measuring the displacement, point 3, if you change point 3, then k 3 1 also will change. So, the influence coefficient depends on both the location of point 1 as well as point 3, but it does not depend on the value or the magnitude of the force applied. It also depends on the direction of the force applied. So, at point 1, if you in the second case you apply force in this direction and then again measure the displacement at point 3, then also the influence coefficient will be different. Okay. So, the influence coefficient has got several property which we can write down. So, it depends on the location of applied force as well as on the location of point where displacement is being measured. All right. It also depends on the direction of the force applied. If you change the direction of the force, influence coefficient is also going to change. But it does not depend on the magnitude of force, because it has to be linear. Okay. And finally, it also depends on what direction we are measuring the displacement. Because you see displacement is a vector quantity. So, it has 3 components delta x, delta y, delta z. So, for each of the components you will have different influence coefficients. Okay. For example, if you come back here, you have x, you have y, and then you have z. Similarly, for the force at 1 you have 3 components, right. So, then delta x at point 3 would be equal to k 31 x x of f x. So, you have 2 superscript on the influence coefficient for the directions of both displacement and the force applied. Similarly, delta 3 in the direction x is equal to k 31 x y f y. So, if you are applying force in y direction, then the influence coefficient is k 31 superscript x y. Okay. Similarly, you can keep on working here. But the bottom line is that the relationship is linear. So, it is also kind of Hooke's law, right. For spring, for example, force is proportional to displacement. Then we also learned about 3D Hooke's law relating stress and strain at a point, but here we are relating displacement at one point to force applied at some other point, and that also turns out to be linear for linear elasticity. Okay. So, this also has got the flavor of Hooke's law. All right. And then the next thing, of course, as we just figured out that superposition is also going to hold. So, if you are applying force, let us say at both point 1 and at point 2, and you are measuring the displacement at point 3, then what would be the total displacement? So, in one case, suppose you are only applying force at point 1. So, we can write down. So, suppose we are only applying force at point 1, then in that case delta 3 is equal to k 31 into f 1. In the next case, suppose we are only applying force at point 2, then in that case delta 3 is equal to k 32 into f 2, correct. And finally, suppose we are applying force at both points 1 and 2, okay, then superposition has to hold because the equations are linear, and that implies that delta 3 is simply k 31 into f 1 plus k 32 into f 2, okay, and this is because of superposition. Because superposition holds. all right. There is of course another way to prove this superposition. So, let us try to do that. So, let us again think of the arbitrary body which is clamped at some locations, and then you are applying force at point 1, okay, and then you measure displacement at point 3. All right. You also have point 2 where you could apply the force F2. Finally, you have force acting at both points 1 and 2, and I want to know what is the total displacement at point 3. So, to find the total displacement, let us break it into different steps. So, in step 1, suppose only force 1 is acting. So, that means delta 3 is equal to K31 into F1, right, as we know that they are linear and K31 is the influence coefficient. Now, in the next step, let us now apply force F2. So, as we apply force F2, the system has changed, is not it? Initially, there was nothing acting on the body, then you applied force F1, the influence coefficient was K31, but now the body has deformed due to the application of force 1, and then you are applying force 2 at the point 2 in the deformed body. Now, since the body has deformed, we expect that the influence coefficient will perhaps be different than K32. So, that means delta 3 would then be K31 F1 whatever was the displacement plus K32 prime into F2, is not it? So, you see we have K32 prime because the body has deformed. So, the influence coefficient may have changed. Okay. All right. Now, in the third step, let us now apply force minus F1. Okay. So, at the location 1, we are now applying minus F1. So, what happens because of that? We will have no force acting at point 1 and we only have force acting at point 2, correct. So, if we go step by step, in the second step both F1 and F2 are acting. So, the body is now in another state, and then you apply minus F1. So, the influence coefficient for 1 and 3 must have changed. So, that would mean delta 3 is then equal to K31 F1 plus K32 prime F2 plus K31 prime minus F1. And notice again that we have K31 prime, which is not the same as K31, because after step 2, when both F1 and F2 are acting, body is in a different state. So, the influence coefficient may have changed. So, we have K31 prime. But finally, when we look at the entire body after step 3, you only have force acting at point 2, right. And in that case, when you measure displacement at point 3, then should not that be equal to K32 F2 because you only have force acting at point 2, and that is the definition of influence coefficient K32. K32 means when you have only one force acting at point 2, then delta 3 is equal to K32 into F2, correct. All right. So, now when you compare these two, what do we get? This tells us that K31 minus K31 prime into F1 plus K32 prime minus K32 into F2 is equal to 0, right. But since this has to hold for arbitrary F1 and F2, the magnitude of F1 and F2 can be anything, right. So, since this holds for any F1, F2, so this implies that the coefficients must vanish, right. So, that means these coefficients have to be 0, which implies K31 is equal to K31 prime and K32 is equal to K32 prime. All right. So, this tells us that in our step 2, when we have both F1 and F2 acting, delta 3 is simply K31 F1 plus K32 F2, or the superposition holds. So, this is another proof for superposition. All right. There is another concept of what is called corresponding displacement. Corresponding displacement. So, again let us think of our arbitrary body, and it is clamped at some point, and you are applying force at point 1 in some direction, and suppose I want to measure the displacement at the same point and in the same direction, then that is called corresponding displacement. The displacement at the same location and in the same direction of the applied force. So, that means this is displacement of the body at the same location where force is applied and in the direction of the applied force. So, that is the corresponding displacement, okay. And naturally it will also have some influence coefficient, right. So, delta 1 is then proportional to F1, where delta 1 and F1 are both in the same direction. See, when you apply force F1, the displacement at point 1 need not be along the direction of force 1. The displacement could be in some other direction. So, displacement here, it could be in some other direction, that is delta 1, the vector, but I want to look at the component of that displacement in the direction of the applied force. So, that is called the corresponding displacement, and that of course, is a scalar. Okay. So, delta 1, the corresponding displacement would then be K11 into F1, and because it is in the same direction as the applied force, it is also called work absorbing displacement, because this is the displacement component which is responsible for work done by the force. the displacement in the direction perpendicular to the applied force does no work, right, because work is force dot displacement. So, we have to take displacement in the same direction as the applied force. So, therefore, we also call it work absorbing displacement. All right. Then the next question is, how much is the energy stored in the deformable body due to the application of force 1? Okay. How much is the energy stored in the deformable body due to force F1? Will it be F1 into delta 1, the corresponding displacement? So, question, would it be F1 into delta 1? So, think of your spring problem. So, whenever you have a spring with spring constant K and you apply a force, suppose F to the spring, then how much is the energy stored in the spring? The energy stored is always half of k x square, right. So, the energy stored is half of k x square, which we can also write as half of k x into x, but k x is nothing but the force. So, this is half of force into x. So, you see force and x is the displacement in the direction of force. So, that is the corresponding displacement. So, the energy stored is force into corresponding displacement divided by 2. It is not force into corresponding displacement. What could be the reason for the half? So, for that you could think that you are pulling the spring very slowly. So, when the displacement is some delta, then the force acting on the spring would be k times delta, and then you have to ramp up the displacement, so that the force applied ramps up from 0 to the force F, correct. So, the force applied is actually varying from 0 to F, and you plot the force versus delta curve, then it is going to vary from 0 to the final force F, correct, when the displacement becomes x. So, the displacement varies from 0 to x and force goes from 0 to F, and in that step what is the work done? That is nothing but the area under the curve, right. So, that is the area of this triangle, which is half into force into x. Okay. So, that is the reason for half. Likewise, here also in case of deformable body, if we apply the force F1 slowly, quasi statically, and ramp it up to the final load F1, then the total energy stored would be half of F1 into delta 1. But then the final energy stored in the body is independent of how you are applying the force. It only depends on what is the final force. So, even if you apply the force instantly, then the body is going to deform, and in equilibrium the energy stored would still be half of F1 into delta 1. But then what is the work done by the agent who is applying the force F1? You see, in this case the total force is acting instantly. So, the work done by the agent would simply be F1 into delta 1, there is no half. So, work done by the agent is F1 into delta 1, but the energy stored is still half of F1 into delta 1. So, where is that remaining half? So, that has basically dissipated because you applied it instantly. So, some part gets converted into kinetic energy, some part gets stored and some part gets dissipated. Okay? But if you do it quasi statically, slowly you ramp up the force, the energy stored is always half of F1 into delta 1, and the work done by the external agent is then also half of F1 into delta 1. Okay. So, the bottom line, the energy stored is simply half of F1 into delta 1. Okay. And then delta 1 is K11 into F1. So, this becomes half of K11 into F1 square. So, that was due to single force, but suppose that now you have multiple forces acting at different points, point 1, point 2, point 3, point 4 up to point n. So, at each point you have forces acting, and you can measure also the corresponding displacement. Then what is the total energy stored? You have to simply sum over the energy due to each of the loads. So, total energy stored is then summation over I equal to 1 to n half F I into delta I. Okay. But now delta I is not K I into F I. So, do not think that delta I is K I into F I. So, that is not the case anymore, because you do not have single force acting, you have so many forces. So, delta I would then be summation of terms due to all the forces, right. So, delta I is summation over j equal to 1 to n K I j F j. Okay. And we can now plug it back in this equation, and then we get the total energy stored. We have double summation over I and j and half of K I j of F I into F j. Okay. So, we are able to write down the energy stored in terms of the applied force and the influence coefficients K I j. All right. Then the next topic is what is called reciprocal relation. Okay. So, is there some relationship between K12 and K21? That is something we want to investigate. So, you can recall K12 would be displacement at point 1 due to the force applied at point 2, and K21 is the opposite. So, we want to know how are those two related, the coefficients K12 and K21. Okay. So, to do that we will work it out through energy. Okay. So, let us think that we have only force F1 acting on the body, all right, and no other force. So, in that case what is the energy stored? So, energy stored would be half of F1 into delta 1, but since only F1 is acting, delta 1 is simply K11 into F1, right. So, this is half K11 into F1 square, and if you think of the body, then here is the body point 1, you applied F1 and the body gets deformed, right, maybe something like this. And the clamped points should not displace. So, suppose that the new point 1 is here, that is 1 prime. So, this is your total displacement delta, that is a delta vector, and then you find the component of it in the direction of the force, and that is your delta 1, the corresponding displacement. Okay. And energy stored is half of k11 into F1 square. Now, let us think of applying the force 2. Okay. So, point 2 was somewhere over here, which may have moved to 2 prime, correct, and we now apply the force 2. So, when we do that, the body again gets deformed, right, and let us suppose it becomes something like this. All right. So, 2 prime goes to 2 double prime. So, maybe somewhere over here, that is 2 double prime, and 1 prime goes to 1 double prime. So, now what would be the additional energy stored? You see, during step 2, you are applying F2. So, in going from step 1 to step 2, force F1 was acting fully, is not it? So, whatever is the additional displacement from 1 prime to 1 double prime, the force F1 acts completely when that extra displacement was happening. So, what is the work done? That simply F1 times that extra displacement, there is no half now. When you ramp up the force F2 slowly, the body goes from red line to blue line, and during that process F1 is acting fully. So, what will be the additional energy stored? So, that is going to be the initial energy, which is half k11 into F1 square plus energy due to additional displacement at point 1, and that is simply F1 into additional displacement. And what is that additional displacement? That is k12 into F2. So, this is the extra displacement. In the direction of force 1. Okay. Plus the work done due to force F2, and since that is being ramped up slowly. So, what is the work done? That is nothing but F2 into the displacement at point 2, right. But you see, this displacement is now only due to application of force F2, because F2 acts after F1 has been applied and the body had deformed. So, work done by F2 will only be in going from 2 prime to 2 double prime, not in going from 2 to 2 double prime, right. So, what is the extra displacement? That is then only due to F2, which is k22 into F2, and this has to be divided by 2, because we are ramping up the force F2 slowly. So, notice that we did not divide this thing by 2, did not divide it by 2. Because F1 was acting fully. Okay. Whereas, this part is the corresponding displacement in going from 2 prime to 2 double prime and not from 2 to 2 double prime. Okay. Likewise, this extra displacement here, this is in going from 1 prime to 1 double prime only. So, the final energy when both F1 and F2 are acting, that is equal to half K11 into F1 square plus half K22 into F2 square plus K12 into F1 into F2. Okay. We can now reverse our step. We say that in step 1 we apply force F2 and then in step 2 we apply force F1, just the reverse of what we did now. Okay. So, we will say let us reverse the step. So, step 1 apply F2 only, then what is the energy stored? That is nothing but half of K22 into F2 square, correct. In step 2 apply F1 also, but when we do this F2 is already acting fully. So, what will be the additional energy? So, total energy will then be half K22 F2 square plus the additional energy, right. And additional energy has got two components. One is due to F1 itself, which we are ramping up slowly from 0 to F1. So, the work done would be half of F1 into the corresponding displacement due to force F1 alone, right, which is nothing but K11 into F1, correct. So, this is due to F1 alone and it comes with a half because we ramped up the force F1 slowly, plus the work done due to force F2, but now you see that F2 is acting completely in step 1. So, the additional work done by F2 would then be simply F2 times the extra displacement at point 2 due to F1, which is F2 times K21 into F1, and there is no half here again, right, because F2 is acting fully. So, what is the total energy here? It is half K22 F2 square plus half K11 F1 square plus K21 into F1 into F2. But you see in both the steps, in the initial step and then the reverse step, the final state of the body has got F1 and F2 acting. So, final state is the same. So, the energy stored in the body should also be the same. So, if we compare these two energy, what we see is that everything is the same except for K12 and K21. So, that means K12 must be equal to K21. Okay. So, that is the reciprocal relation, K12 is equal to K21. Okay, let us work out another interesting relationship, that is called Maxwell Beatty Rayleigh reciprocal theorem. Okay. What we worked out just now was reciprocal relation. Now, we will work out what is called reciprocal theorem. All right. So, suppose that we have again our body which is clamped at some locations, and then we apply force at let us say n points in the body. So, we have n points, point 1, point 2, point 3, point 4 and then point n, and we have various forces. So, we have F1, F2, F3, F4 and F1, and we also measure the corresponding displacements at each of the points. Okay. And in the second case, let us again apply forces at those same n locations, but of different values. Let us suppose F1 prime, F2 prime, F3 prime, F4 prime, Fn prime, and then again measure the corresponding displacements. Okay. So, we have two situations, situation 1 and situation 2. So, here we have F1, F2 up to Fn and then delta 1, delta 2 up to delta n, and in situation 2 we have F1 prime, F2 prime up to Fn prime and delta 1 prime, delta 2 prime up to delta n prime. So, they are the corresponding displacements. Okay. So, what this theorem tells us is that the work done by forces in situation 1 through the corresponding displacements of situation 2 is same as the work done by the forces in situation 2 through the corresponding displacements of situation 1. Basically, you have to do the cross product here and it gives us the same value. So, what it tells us is that summation over I f I delta I prime is same as summation over I f I prime into delta I, and in words, work done by forces in situation 1 through the displacements of situation 2, the corresponding displacements, equals the work done by forces in situation 2 through the corresponding displacements of situation 1. Okay. the proof is not so hard. Let us try to do that. So, we have the left hand side is summation over I f I into delta I prime, right, which we can write as summation over I f I, then summation over j k I j f j prime, is not it? And if we expand it slightly, then this is f 1 into k 1 1 f 1 prime plus k 1 2 f 2 prime plus dot 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 up to k 1 n f n prime plus f 2 into k 2 1 f 1 prime plus dot 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 up to k 2 n f n prime. So, we keep on going up to f n into k n 1 f 1 prime plus dot 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 up to k n n f n prime. Okay. Now, let us collect the first terms from here, now, for example, this term, and see what it is. So, this term here, you see in each of the terms here we have f 1 prime as common, right, you see. So, we take it out and write the remaining things. So, we have f 1 prime into k 1 1 f 1 plus k 2 1 f 2 plus dot 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 plus k n 1 f n, is not it? And then we can use reciprocal relation to say that k 2 1 is same as k 1 2 and k n 1 is same as k 1 n. So, this is then f 1 prime into k 1 1 f 1 plus k 1 2 f 2 plus dot 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 plus k 1 n f n. And what is the thing inside the bracket? That is nothing but delta 1, right, corresponding displacement at point 1. So, this then becomes f 1 prime into delta 1. Okay. Similarly, you can collect the coefficient here, and that is going to give you f 2 prime into delta 2. So, likewise, when you collect all the coefficients, you simply get the right hand side as summation over I f I prime into delta I. So, that is your reciprocal theorem. So, till now we only considered forces and displacements. We can also have moments and rotation. So, the work analog of force is displacement, the work analog of moment would be rotation. So, we can think of a arbitrary body again, and we have various points 1, 2, 3, 4, 5, 6, and we can apply forces at some points f 1, f 2, f 3, and other points we could apply what is called moments. Okay. So, here for example, we can apply moment m 4, m 5, m 6, and we can measure then the corresponding rotations, the rotation in the same direction as the moment, just as for the corresponding displacement. So, we will have corresponding rotations here, and then the corresponding displacements also, of course. So, moments would be like generalized forces and rotations would act like generalized displacements. Okay. So, moments are like generalized forces and rotations, which let us say is theta, are like generalized displacements. All right. And if we then think of in terms of generalized forces and generalized displacement, then we need not differentiate between force and moment or displacement and rotation, and our entire formula would simply hold as it worked for just the force and displacement. For example, if you want to measure the corresponding rotation at point 4, then theta 4 is then simply k 4 1 into f 1 plus k 4 2 into f 2 plus k 4 3 into f 3 plus k 4 4 into m 4 plus k 4 5 into m 5 plus k 4 6 into m 6. Okay. The formula holds as if we have only force and displacement, but then the dimension of the influence coefficients are of course different. This, for example, what is the dimension of this? So, this has to be theta, which is non-dimensional, divided by force. So, this is theta by force, right, whereas this is theta by moment. Okay. We can also find out the displacement at point 1, for example, the corresponding displacement, and then delta 1 is then k 1 1 into f 1 plus k 1 2 into f 2 plus k 1 3 into f 3 plus k 1 4 into m 4 plus k 1 5 into m 5 plus k 1 6 into m 6. And then what are the units of k 1 1, k 1 2 and k 1 3? So, this is, for example, displacement by force, okay, whereas k 1 4 is displacement by moment, but we know that moment is force into displacement, right. So, this is equivalent to rotation, which has no unit, right, over force. And again here also we can say that k 1 4 is same as k 4 1, the reciprocal relation. So, here also k 1 4 is same as k 4 1, and you can see that dimension is also matching, right. You see this has the dimension of rotation by force, and k 4 1 has also got dimension of rotation by force. All right. So, the entire thing that we worked out would work in the same way. We just think of in terms of generalized force and generalized displacement. All right. So, with this I am going to end the lecture today, and we will then continue in the next class. Okay. Thank you.